us?
Yeah, he said you can hear you.
Okay, great. So this is the XDP Workshop. We have a very slight change in the agenda. So Emily will start, and then we will change the presentation. So I will start sharing the slides from my computer, and then this is when the Mate will take ownership remotely. So please start.
Okay, sounds good. So I'm Emily Wagner. I'm going to talk about some of the work that I did at my previous company, which is sadly no longer in business, but for a brief period of time, there were customers and XDP was a central part of the product. It was basically a global acceleration network built using XDP. There was 115-ish POPs across the world. And the target market was real-time applications like gaming or video and voice chat, anything. Typically most of the customers were UDP, but it was a protocol agnostic network. So in general, when a customer contracted with us, they would basically tell us their IP import or IP imports that they were hosting their service on. And in exchange, we would give them a Subspace IP import, and then they would either point their DNS records to this new allocation, or just tell their, for example, a game client to talk to that allocation. So when their end users went to go access their service, they would end up with using the Subspace network. Basically, they would go through the Subspace network first, using a globally optimized Anycast networks. And so, as you might imagine, there was a bunch of people whose full-time job it was just to figure out how they were accessing, basically if they were being assigned to the correct POP. So each of those POPs was very bare bones. It was basically one commodity hardware machine. There was no switch, there was no router. You just took an ISP link and plugged it directly into the machine, and you would have multiple of those to have better path diversity. So each hop could have improved latency, reliability, and availability based on this path diversity. So now the XDP part, now that we have kind of set the stage of what this product was. So once they arrived at that first ingress hop using Anycast, at that point forward, we would basically be using this XDP native protocol to traverse the network. So the first thing is, given that IP import, who's this end user targeted for? Who's the customer? So you look that up, and then that points you to a specific egress node that the customer is assigned, basically based on their location. And then you can find the best sequence of POPs from ingress to egress based on real-time telemetry. So now we have kind of where it's come into the network, where it's supposed to leave the network, and the path it's supposed to take through the network. Now we're kind of ready to basically stamp that whole thing on the packet using XDP adjust tail, basically extend the end of the packet. We want to leave the beginning of the packet untouched because we don't necessarily control every routing device within this network. We end up basically we might have different types of uplinks. It's not just like we've contracted fiber and everything's like a layer 2 tunnel. There's going to be layer 3 devices en route that we don't control. So the trailer kind of basically contains the path through the network, as well as like session specific information like the client and the server. So that way, the ingress and the egress will have kind of the smarts, but just like the internet, the middle is not smart. All the middle has to do is look at that sequence of nodes and leave the packet untouched. So obviously we're extending the packet. We have to update the checksum and the length at the ingress and the egress as we add and strip this trailer. But in the middle, we just forward it. So this, you say, well, this path is fixed at the source. What if there's failures in the middle? And we basically, in addition to this, source-based node-by-node routing, we end up selecting the best ISP pairing at each hop at the time of forwarding. Again, using that same real-time telemetry that we're hosting at each POP. So we are able to react to network outages, even if it looked like the POP was fine, and there's a failure en route, we can actually end up selecting a different link. And we're using XDP redirect because we don't have a switch, we don't have a router, we're basically moving between ISPs using that redirect functionality from one port to another. So this means that any individual node or ISP can fail or be taken out of service, and the network will heal with no or minor packet loss. Now, I would say the most technically challenging part of that was figuring out how we could take out the egress node that's maintaining that direct server connection without resetting the connection for the user. So obviously, we need that IP import to remain fixed where it is. How do we end up, we don't want to necessarily share global state about every session in the whole network. So how do we end up sharing that information between POPs? I didn't make slides on this, I was told to keep it real short, so, but I can definitely talk about it if people want to hear more about it. But basically, we had a specialized protocol that would bounce the information between egress POPs so that you could migrate the session seamlessly and the customer wouldn't know, other than having slightly degraded latency for the time of the maintenance. So on top of this kind of basic tunnel functionality through Subspace, we built peer-to-peer relays. So for example, if you were having, one of our customers was like a video voice chat, sort of like Second Life kind of thing. And for them, we had this peer-to-peer relay where, there was no server in the middle, but we could pair two tunnels together. And then the clients could talk directly to one another without needing to do NAT traversal and that kind of thing. We also had customers who were interested in load balancing. So, kind of classic, right? They have multiple servers in one region, or they want us to provide regionalization for them. So they don't want to have to manage multiple regions, and having to figure out where a given end user is supposed to go. So again, one IP and port, we figure out where the customer is located and get them to the right egress group, and then load balance among those egresses. So yeah, I'm happy to take some questions. I know that's a lot of information in a very few slides, but I could talk about anything that's of particular interest.
Okay.
All right, thanks.
Oh, thank you. Yeah, it's great to join the XDP workshop again. Can you go to the next slide? Okay, and actually, last year in the XDP workshop, we introduced the idea of XDP extension with accelerator QAT. So in this year, we have got some progress, and we think it's good to share some performance number and also share some topic to be discussed. And first, I think we can. Our agenda includes mainly 4 parts. The first is the first 2 parts are some brief retrospective about this idea, and the third part is to share some performance number we have got by now, and the fourth part is there is some discussion about the redirection method to accelerator. There may be two options. Can you go to the next? Can we move to the next page? Okay, thank you. Okay, let's have some brief retrospective. This idea is initiated to unlock the XDP capabilities on the encrypted package with the accelerator QAT, because now for the security and privacy, more and more encrypted package in the network. So, but the XDP only works on the plain text, the packet data. So we would like to unlock the more capabilities of XDP to process the encrypted packet. But as we know, the XDP runs before packet data touched by kernel networking stack. So there's no decryption functionality in the XDP layer. So we have an attempt to use the hardware-based accelerator to enable and accelerate the crypto in XDP layer. Okay, this is why we need it. Okay, please next. Yeah. This is an overview about the XDP inline accelerator. For our implementation, it compromised of mainly three parts. One is the accelerator device map, and the second is the XDP redirect accelerator adaptation, and the third is accelerator XDP driver. For the accelerator device map, its entry specifies the mapping relationship of a specific flow and its corresponding accelerator device instance, because this flow will be processed by that specific device instance. And this entry also contains the context of some crypto material for the specific flow. So the accelerator map framework will also export a set of unified operation callback function for the accelerator device to register or unregister its own implementation. The pre-processed XDP eBPF program will be called in the network device, and if the BPF program decides the packet will go to the accelerator, it will identify the accelerator device instance based on the packet header information or other private information. The XDP redirect accelerator adaptation is to modify the current XDP redirection implementation to adapt to the accelerator drive map. The XDP frame will be included in the specified accelerator device instance. Also, it supports load balancing of the in-queue operation, the accelerator's in-queue operation to a remote CPU call by a specific software FIFO. And the accelerator XDP driver implements the operation functions for the accelerator device. It includes such as the packet data in-queue, interrupt the accelerator device, interrupt handling, polling, like a socket buffer construction and injection to kernel networking stack, and also XDP buffer submission to AFXDP RxQ. And there is a post-process XDP program will be running in the context of accelerator XDP driver. So after the post-process program, the packet will may either go to the path 5 for packet drop or path 6 for AFXDP based kernel bypass, or the path 7 is kernel networking stack injection, or the path 8 for the packet forwarding. And we can also see the legacy path 1, 2, 3, 4 for XDP and AFXDP could coexist with the new model path that is 5, 6, 7, 8. That means, for example, one user may have different flows. Some flows want to be decrypted and then go to the user space, and the other plain text flow may just want to go to the kernel networking stack. So it could support some different permutation about the different paths. Can I go to next? Okay, this part is we totally have 3 use cases for our experiment. The first one is about the comparison. between the QAT XDP solution and the QAT LKCF solution. If we check the figure on the left, we can see the QAT XDP data path is when the packet is received in the NIC driver, and then it will be redirected to the QAT device directly. Post the decryption in QAT, then the QAT will inject this packet to the kernel network working stack, and especially because the packet has been decrypted by the QAT, so we have to do some bypass in the kernel network stack. That means the kernel ESP crypto will not decrypt the packet. For the QTL-KCF, QTL-KCF actually is now in the upstream kernel. That is, it follows the legacy IP transform and ESP crypto LKCF framework, but it just offloads the decryption operation to the QAT in the LKCF ESP crypto layer. And then it will continue the path in the kernel network. And our experiment showcase the performance statistics showcase that the QAT XDP solution has about 21% performance gain for the TCP case, and about 5.3% performance gain for the UDP case, compared to the QAT LKCF solution. In this experiment, we can see the QAT XDP solution is feasible, and with both cases just use one QAT instance, and the QAT XDP solution demonstrates it has better performance than the QAT LKCF. Can you go to next? The second use case is about the IPsec packet drop post decryption. The ESP packet of IPsec tunnel mode will get redirected to QAT for decryption. Based on the decrypted inner header, the packet are discarded before they reach the Linux kernel networking stack. Here we have some number is the XDP drop rate post decryption could reach above 13 Gbps with the packet loss rate less than 1%. Actually, the decrypted inner header can be used for various use cases. Because there may be some outer header. You have some outer IP, but in the inner header you have its inner IP, and from that IP we can maybe we can have different. We can do different things such as DDoS prevention or rate limiting, routing, forwarding, load balancing, and we can do a lot of things based on the decrypted inner header. And currently, the XDP this drop occurs in the context of QAT XDP driver. So we are also investigating if this drop can happen in the QAT device without triggering any interruption and software processing. In that case, we would expect the drop performance could be higher, and it could save more CPU core resources. Can you go to next? The third use case is about the AFXDB user application post decrypted packet. This experiment is to verify the packet reception in user space for the IPsec flow. Okay, we have two patterns. The pattern one is we have the NIC and the QAT related operation on the same CPU core. That means the NIC interrupt NPI processing, the QAT enqueue, dequeue, QAT interrupt, and also the enqueue packet to the RxQ of AFXDB will occur on the same CPU core. It can benefit from the cache locality and reduce the call-to-call communication. So we can achieve about the 15.8 Gbps with about 1.07 cores consumption. And in the pattern two, we are attempting to explore a better performance with more CPU core usage. That means the NIC operation and the QT operation will have different core affinity. And we use this pattern too. We can reach up to over 20 Gbps with about 2.34 cores. Also with packet loss rate less than 1%. Okay, this is a QT XDB inline AFXDB case. So we totally have the okay. Well, one more thing I would like to check is the pattern 2 also have some overhead about the cache locality and core communication. And in the figure on the right, we can see pattern 2 can reach higher performance, but it has gained 5.1 Gbps enhancement, but the cost is 1.23 cost increment. So pattern 2 has its price. Okay, well that's our performance number update, and can I go to the last page? Okay, our current implementation is based on the XDP redirect. We add accelerator dive based on existing dev map. That means the dev map will have two kind of device. One is Netdev, and the other is accelerator dive. This is one method to redirecting the packet to accelerator, and another option is to use the BPF kernel function directly. In this one, yeah, both methods has its advantage and disadvantage. I just list them in a table as per my knowledge. Okay, that's my introduction. That's my update about the QT XDP topic. Oh, maybe it's over.
Here we go. All right. So this presentation is partly a repeat of the one I did at the other NetConf without the Netdev, but the NetConf thing that was co-located with kernel recipes, but this one to a broader audience, I guess. So apologies for those who've seen it before. I will try to run through this a bit quicker, and then I added some status update on the whole queuing thing at the end as well. So this was just to have the whole idea with this was to sort of give a status update of what's been going on with XDP since the last NetConf conference, which was in 2019. So this is all this sort of major development we've seen in XDP in general. So finally we've seen multi-buff land. We have RX side XDP hints. We have feature flags, which is the ability for drivers to declare which parts of XDP that they support. We've gotten some more stack helpers to call into the networking stack, like contract and synproxy. We've gotten a lot of improvements to XDP redirect. We have multicast support. We have mapped lookups, so you can actually check if your redirect is going to work ahead of time. There's a hash map type. There's some performance improvements. You can now have programs inside dev maps and CPU maps, which means you can perform, you can execute a separate, for the dev map use case, you can execute a separate XDP program after the redirect, so based on the egress device. And for the CPU map, this allows you to do things like software RSS scaling. Then there's more performance work on eliminating indirect calls. We have a live mode in BPF prod run, which is used in the XDP-based traffic generator. That's in XDP tools. We have this AFXDP need wake up mode for user space applications that want to busy poll. And then we have some improvements around also atomic replace of the program attached via netlink or BPF attachment that locks out other netlink or other attachments. So that's sort of just a general overview of all the high level stuff, just so people are aware what's actually going on here. Next slide, please. Oh, okay. I see now that this is the wrong version of the slides. Anyway, this is what I wanted to show. I think, yeah, okay, never mind. This bit is the same. So I compiled this list of all the driver support, where you can see that we now have, I think it's almost 40. Is it 39 drivers with XDP support in general, and none of them have all the XDP features enabled by default, as you can see. So the check marks in parentheses is features that you can turn on and off. So mostly this is on the TX side. This is things where you have to enable TX for like the Intel drivers, and for Mellanox 5 you can turn on the whole thing or off. And some drivers are just configuration dependent on whether or not they support XDP at all. But you can, this is all based on the feature flags in the stack. So you can query these and see what's going on. Next slide, please. Okay, and then we have some different ongoing work. I believe we will hear about the first one after this. Jesper has been working on some VF optimizations, because turns out containers is a thing, and we want to be able to call to put XDP frames into containers and have it perform reasonably well, and that is not always the case today. Then there's multiproc attachment, which we discussed at NetConf, and there are some improvements to the whole multiproc thing that need to happen first, mostly for performance reasons. Right now, mprog is based on indirect calls, which is not going to really fly for XDP. Then there's the queuing work, which I will touch upon later. Next slide. So a bit more detail on some of these. For generic XDP, we also have had some discussions around just improving the performance of this in general. Now that we have multibuff, we can actually do GSO on generic XDP. And like, generic XDP is this weird stepchild that was created initially only for testing things, and yet people either accidentally or deliberately use it anyway. So it's sort of, should we improve the performance of it, or what are we going to do? But these are some of the things we could improve. The last one is actually part of the VF work, where the implementation of TX side for generic XDP handles HKBs, so converting the VF driver over to using that when it sees that it's handling an HKB could be one way of improving the performance. Yes, next slide, please. Then we have the AFXDP XMID path. So this is the first two here are related to the non-zero copy mode, where there's this kind of strange thing where some drivers implement AFXDP zero copy, which on TX means that the driver implements a separate NDO for transmitting packets. But for all the drivers that don't do this, notably VF is one of them, we allocate an HKB, which is even socket allocated, which means that it's sort of part of the socket memory allocation tracking for the socket structure, which is a bit redundant when we're talking about pre-allocated AFXDP buffers. And actually, why do we need to allocate an HKB at all when we're just transmitting out an XDP frame? So I'm hoping to see some improvements on this side, which could help with getting the so basically the goal here is to get the overhead of running AFXDP on a VF inside a container as low as possible. We're not going to be able to do zero copy all the way down, but we can hopefully limit it to one single copy, which may still be pretty acceptable performance, way better than going through the stack. And it allows you to have to not have to mess with things like SRIOV to run an AFXDP application inside a container. And then there's the TX hints, obviously, which again, I think Stanislav is going to talk about after this. So next slide. Then we have the XDP hints in general. The initial implementation was only for a few metadata fields. I think we've already seen some work towards adding more. I'm sure we will see more of this. Then we have the XDP redirect use case for this. So right now, when an XDP program is running in the driver, it can access the hardware hints through the special kfuncs, but as soon as the packet is redirected somewhere, it all goes away. And so the XDP program has to, when it's operating in the hardware driver, it has to save them somehow. And right now, you can do this by just writing it in the metadata area or whatever you want to do with it, but there's no really standardized way for it. So for example, an XDP program running again on a VF will have to have some out-of-band communication method to speak to the host side XDP program. And also after redirect, if we end up creating an HKB of the data, which we do in CPU map, for example, or again, if we redirect into a VF, then the stack does not have all the hardware metadata anymore. And the hardware drivers will usually in the regular HKB path, they will populate the HKB metadata directly from the hardware descriptor, which is also not available after an XDP redirect. So Jesper had this idea of finding some standardized, some storage area somewhere in the HKB shared info or something, and sticking it all there, like opt-in, so the XDP program can just go save stack metadata or something, and then after the redirect, you will still have this available for building HKBs. And then the last thing is this bit annoying thing where we ended up calling it XDP metadata and not XDP hints, which was the sort of working name that we were using during the discussions. There's an XDP hints mailing list and so on. But if you look for XDP hints in the patches or the Git log, there's nothing there. It just says metadata. And if you Google metadata, you get all sorts of stuff because we have lots of different things that are called metadata. I don't really know what to do about this. Maybe just add some documentation or something to resurrect the XDP hints name. Right. Next slide.
By the way, Toke, we have to speed up a bit if you can.
Yes, this is close to being the last one, since I think the last slides are maybe missing. Anyway, data pair tables, build from, yeah, so this was just some ideas for my view of what we want to do with XDP is to be able to transparently run a data path software acceleration where you can just turn it on and it will call into the stack and with the features that you need. And right now we have contract lookup, we have fib lookup, but we're missing bridge, we're missing net filter flow tables acceleration to be able to do this. And there's some ongoing work to do here, but this was just to give an idea of where I could see this going. Next slide. Yes, and this one was the wrong one, so just skip that one. And since if I'm running out of time anyway, I'm just gonna have to skip the queuing bit. So I can just say a few words about the update of the queuing. Sorry for sending the wrong slides, but basically the update is I talked about this at LPC last year. And it stalled out a little bit, the work. One of the things that turns out to be really important is having something like BQL and having some way of limiting the amount of data outstanding in the hardware queues. And I have some ideas for this, centered around adding a trace point callback in the XDP return frame. Which allows a BPF program to sort of basically re-implement what we're doing in BQL of programmatically tracking outstanding data in the hardware queue and limiting it so that we can keep stuff queued in the stack or in this XDP queuing feature. So yeah, I had some nice diagrams about this, but it seems I sent the old slide deck, so sorry about that.
Okay, I guess Toke has to have all of the questions offline and we have to switch directly to Stanislav.
Okay, cool.
Thank you. Yeah, I have 2 slides. I don't think I will take too much time.
You also have just 9 minutes, so.
Yeah, okay. Yeah, I think I'll finish faster. For me, I'm not going to talk in too much details about the particular offloads. I'm going to do a more in-depth presentation at LPC about XDP and XDP offloads. But here I just want, again, probably to spend time asking 2 questions. And if someone has some ideas, you can reach out to me and we can talk. So can we go to the next slide? Right, so in the past year, we've added we've added receive side metadata. I don't know. I guess I agree with Toke that the name is unfortunate. Even the hints I don't really like. I guess the offloads would be a better word. This is like offloading some of into the harbor or reading some harbor offloads. But whatever, yeah, the thing that landed on receive is at XDP level, we now have BPF helpers that you can call and receive information about the packet that the harbor has. This is for our internal and external cases, which cannot really use AFXDP or XDP because of a bunch of limitations, right? Over the past years, some of them have been addressed. Things like SG, multi-buff. We've added receive checksums and timestamps. We're almost done with the transmit side of things. I have work in progress patches from Song from Intel about AFXDP departure time offloads. Some of the things that I'm thinking maybe we can also follow up with TSO. I've seen some TSO discussions on the list, but this one, I don't know. People don't seem too happy about TSO. They think that we want to offload TCP and compete with the kernel, and this kind of gives strange vibes. So I don't know. This one we might discuss more. And the other thing that we might also be interested is if and when PSP lands in the kernel, there also might be good case to have some TX crypto offloads. I've heard the talk about a QAT. I tried to reach you separately in the chat, but I cannot. I have a bunch of questions. But yeah, something that does crypto would be also nice. I don't know, because QAT seems to be a separate device. And here, I don't know. Okay, this is for the offloads, right? We have RX, and we will have hopefully TX soon. I'll do 1 or 2 respins. I don't see any questionable feedback anymore. So hopefully the TX goes as well, and we can follow up on what I have on the list. So next slide, please. And the other thing I want to also highlight and maybe get some feedback is the point that Toke also mentioned in his previous talk is it's pretty hard to understand which device supports which offloads. So at least for TX side of things and for AFXDP side of things, I was thinking that maybe we can repurpose XDP hardware metadata tool that I have right now that prints the offload. Maybe we can have some mode where it can run as a qualification tool, where it basically tells you your NIC supports this offload and gives you passed or not passed thing. It might kind of be. Go ahead.
We already have a tool that was meant to do this around the XDP features thing, which
the features though is feature very it's very manual, right? You set the bits and
yeah, but we included a tool in the self-test which has a test mode where it will run a packet through, it loops packets through to a device under test, and it checks if the features that the driver says it supports actually supported. And that was explicitly to have exactly what you're asking for here. I don't think anyone is actually running it, but it's there, and I think it can be quite straightforwardly extended to the metadata. And then we just need to get some CI to run it. We're working on getting that into the Red Hat CKI stuff, but there's a few steps left before we get to that, I think.
Okay, awesome. Then I'll look into it. Yeah, because other thing that also would be nice to have is the CI, maybe even CIs with the vendor hardware that we can run all this more real hardware stuff on them. Because right now, at least for BPF, all the CI is in the VMs, and it's all software-based paths. Okay, yeah, then
Hello everyone, I'm Xuan Zhuo. I'm from Alibaba Cloud Operating System Network team. Today, I'm so excited to talk about my work about regarding Net. I will let me skip this some test. Can we skip this? Can you hear me?
Yes, but Alex said that we don't have time. So I'm not sure, Jamal, can we extend this by 5 minutes? Okay, so go ahead. But you have just 7 minutes, okay?
Okay.
I should say we also have breakout sessions. Any of these rooms can be booked, and there's much bigger rooms. We have an official breakout sessions Thursday and Friday, so this can be extended as well for then for Thursday or Friday.
Yeah.
Okay. Okay, should I continue? Okay. Okay. The Net didn't support the vehicle reset. This is important to XDP socket. We need that to release the buffer fed to the ring, and when we bound the XDP socket port to the ring or unbound us, this is common ability to most physical network headers. So we introduced a new feature to the Vital spec 1.2. After that, the Net has the ability to support the XDP socket and the ring resize. That is not only for Vital spec. For Vital Net, is also for another Vital devices. So the XDP pushes the progress of the Vital spec. The Vital Net supports in place next. Okay, the Vital Net supports RX partial system. If the sender wanted to offload the TX system and the receiver on the same host. The hypervisor will transform the packet with order calculating the CSUM. The receiver will get a packet with invalid CSUM, but the packet is valid. So that is a trouble for the XDP to handle such packet. We tried to calculating the CSUM inside the driver after XDP processes, but we must change the XDP core to support the XDP TX or reductor. As I know, just Wagner has this problem, so we gave up this way. We tried another way, introduce a new feature to Wagner spec to let that device to calculate the CSUM. Then the driver will not receive any partial CSUM packet. We want to change the worker from the above the picture to the another picture. The CSUM of every packet will be calculated by the hypervisor. This is okay for DPU. We will use the FPGA to do this. For the FPGA, that will not occupy too much resources. The DPU network devices will work more like a physical network card. This will be friendly to XDPU. My colleague Kenji is pushing this work. Okay, let's please. I think I have not too much time. We can skip this. Okay. We know that Wagner spotted XDP before we first on this file. I started this work by XDP socket. We want to inherit HTTP3 by the UTP. We want to do that by XDP socket. We will say more about that later. In 2020, Wagner didn't support XDP socket and even the VQ reset. So we implement the XDP socket 0 copy for Wagner internally, and we apply that on large scale. In 2022, we fixed the trouble. We cannot load XDP with no more queues because the default model we must give every CPU a queue for TX. As I said, the number of Wagner queues is fixed, so we must share TX queue. And on most cases, we load XDP and with all the XDP TX. In 2023, NG spotted multi-buffer XDP. We use that for our jumper frame, and we refactor XDP code. Now I'm pushing XDP socket 0 copy to the upstream. This is a long story. I will show more on next page. In future, overall, we will continue to make the Wagner be friendly to XDP. Okay, next please. This is a long story, but I have more time. I spent 2 years to let the Wagner support the XDP socket 0 copy. I first said the Wagner did not support the VQ reset. So I spent about 4 months to let the Wagner spec support the VQ reset. Then I spent 7 months to let the kernel, QMR, DPDK to support the VQ reset, and I refactored the XDP code of Wagner driver.
Yeah.
After that, I spent a half year to make it. Okay?
Yeah, Zhan.
I'll spend
Yeah, we are just
okay.
out of time, so
Yeah.
thank you for all for. Sorry.
Oh.
Yeah, there's breakout sessions, right?
Yeah. Okay.
This can be continued at breakout sessions on Thursday and Friday. We have quite a lot of time there.
So Alex, that's an AR for you to organize the thing in the breakout session. And thank you all for attending, and thanks to all of the presenters for showing up and sharing their status. Thank you.